We are now on the Lab 8 of our multi-day workshop, which involves the servicing of the ADC with DMA. This activity involves the familiarization in the operation of the DMA. But before we proceed on the workshop itself, we have to identify what DMA is all about. When we say DMA from the word alone, direct memory access, this is the method of transferring data. It's either sending or receiving from the computer RAM to another part of microcontroller system without using the CPU. In other words, we will be bypassing the process involved in the CPU. DMA can save the processing time, and it is more efficient, faster in transferring data. In order for us to use the DMA, we need to assign a DMA channel. This DMA channel used to communicate data between the peripheral device and system memory. Ideally, DMA can read data from the different registers. This involves the ADC, the transfer to or from memory blocks, the IPC, the EMIF, and other. So at first, in this activity, we'll be using the ADC channel A0 will be buffered using the ping pong style trigger, and our trigger for this activity is to get an EPWM1A. Figure here explains how are we going to start our activity. So at first, we have to import a project from our previous activity. So this is how we import a project. We just go on to our CCS, just click here, File, Import, and then you have to choose here the CCS project. And after that, you will have here the Import CCS Eclipse project. Then we have to browse it here and look for the lab number 8. And then just simply click this folder and then select, and then after that, finish. Once we import the Lab 8 folder here, as you notice when you click the arrow on the right part, so you can see here the different components, which involves the C program file, the CMD, and of course the assembly of our program code. Going back to our procedure, after we import here, we'll try to inspect the lab8.cmd, because ideally when we say DMA, it's a direct processing from your peripheral output going to your memory blocks. That is why we need to inspect what's the content of our lab8.cmd. This is the linker command file. And it says here, the section called DMA memory buffs is being linked to RAM/GS4. So let's go to our Lab8CMD. And then let's double click this one, and we have here, which actually have on the lowest part, we have here the DMA memory buffs. But what is this DMA memory buffs? This is a user-defined sections wherein we provide a specific memory blocks for this DMA memory buffs. So let's try to check what is specifically the content of this DMA memory buffs. So we can check here on the main, I guess. So let's check in main. So this is the main 8.c, or in other words, this is the C program code, the main C program code. This include of all files. You have here the header files, and then other components, the initializations of your CPU, peripheral, and to enable other interrupts. But what we need right now is the DMA memory buffs you have here. And as you notice, we have also the pragma. This is a directive. This pragma here is a special purpose directive which gives or provide an additional information to the compiler. So we have here the pragma, the data section, which involves the content, the ADC buff row, and the DMA memory buffs. So this one, we already allocate the DMA memory buffs, which is located to your RAM/GS4. As you notice here, you have here the link to DMA accessible memory. After we inspect our CMD now, we are now ready to modify or set up the DMA initialization. Let's just double click the DMA here in this one. And we are now on procedure number 3. So we have to edit the DMA.c using these different conditions. Let's take a look on this one. Configure the DMA channel 1 mode register, or the MODE, so that peripheral interrupt source select is set to channel 1. Enable the peripheral interrupt trigger and set the channel for interrupt generation at the start of transfer. Configure for 16-bit transfers with 1 burst per trigger and auto reinitialize at the end of the transfer. Enable the channel interrupt. Configure the DMA trigger selection register so that ADCA interrupt 1 is the peripheral interrupt trigger source. In the DMA channel 1 control register, clear the error and peripheral interrupt bits. Enable the channel to run. This portion is very much essential in writing or modifying the DMA components or structure of our C program file. That's why we have to check here on how to configure the DMA channel 1. As you notice here, the DMA registry, the device register, which includes the CH1, mode, and all. This value here, we cannot just simply check or define without basing it on the datasheet. So we have to go over on our datasheet by just simply copying the device register. So we have to copy this one, the DMA regs, and let's proceed to the datasheets. So you have here Control F and then Control V. So the device register is DMA regs, and the register name is DMA underscore reg. So we have to get this one. Control C and paste it here. So we have here the different DMA registers. Just scroll down. Let's try to identify. Here, the DMA channel registers is located on this part of your datasheet, and what we need right now is the mode register. So after we look for the DMA registers, we have here the DMA channel registers, which includes the different acronyms and register name. But what we need right now is the mode. So let's just click this one, go, and you have here the different filled sections of your mode register for DMA. These bits, in every bits have equivalent value. Let's take for instance, this bit number 15 has a field of channel interrupt enable. This is how we provide an information on our CCS. Let's take for example this one, bit number 15, which has a question mark, and that is channel interrupt enable. Usually if you want to enable or disable a data, you just need to put 1, means enable. So you can just put right here enable, and 0 it for disable. Looking back to our procedure, that's written here because we want to enable the peripheral interrupt trigger. So this will be our basis. We want to enable the interrupt. So let's put here the value equal to 1. Next is the data size. So what will be the data size? Bit number 14 is a data size, and we will be choosing it's either 16-bit or 32-bit. Based on procedure, we need 16-bit. At this point, we have to configure for 16-bit data transfer. Therefore, we have to choose 16, which has a value of equal to 0. In the CCS, we can write here 0. Next is reserve. So if you notice or observe some components which are reserved, just keep it 0. Since we have 2 bits here, you put 2 zeros. And the next, continuous. If we want to stop, we have to put the value 0, but if it's reinitialized, meaning it's a continuous process, so we have to put the value equal to 1. The procedure, it says here auto reinitialization, meaning this is a continuous process. Therefore, we can write it here equal to 1. Next, the one shot. We have here the 1 burst per trigger. This will be your reference in writing or coding for one shot bit. So 1 burst per trigger, what the datasheet says, meaning if we put the value equal to 0, that means 1 burst per trigger. And if it's the value equal to 1, means all bursts are triggered. But what we need here is a 1 burst per trigger, so we have to put on the CCS the value equal to 0. In our bit number 9, we have here the channel interrupt mode. So we have to fill this one, it's either 1 or 0. So going back to our procedure, it states here that the channel interrupt generation is at the start of transfer. In our datasheet, bit number 9, the interrupt will generate at the beginning of new transfer, that's equal to 0. And to generate an interrupt at the end of the transfer, it's equal to 1. Therefore, we have to put on the CCS the value equal to 0. Next bit is the bit number 8, involves the peripheral interrupt enable. Since we are dealing with interrupt and we want to enable, just simply put equal to 1, 0 for disable. So for the overflow interrupt enable, as we notice on the procedures, there's no such thing as overflow flag, meaning if there's no condition written in the procedure, meaning we have to assume that the value is in its reset mode. The reset mode always for any of this field is always equal to 0. Therefore, we have to put here equal to 0. The next bit, 6 and 5, are reserved. So let's skip this 0, 0. And the last bit here, 0 to 4, and we are working on channel number 1. Therefore, we have to put the value here, channel number 1, which has a value of 1. Since this is bit 0 to 4, so there are 5 bits. In writing the value or the binary code for this channel 1, it should be written as 0, 0, 0, 0, 1. This is how we provide details on the different bit components of your channel 1, starting from your bit 15 to 0. But how are we going to define this bit value here? I have here the DMA registry for all channel 1 mode, but what we need to do here is the hexadecimal value. As you notice here, the bits from 15 to 0 has a value of 10, that's in binary, but what we need is hexadecimal. The first thing we're going to do here is to copy all these values, the binary values from 15 bits to 0. So we can copy here 1, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 1. So this is now the equivalent binary numbers or binary component of our registry for DMA regs channel 1. And then we can just simply convert this one into its equivalent hexadecimal. Let's check on the internet. Let's copy this one. Simply copy and search here binary to hexadecimal, and we have here. So just simply paste it here and let's convert. So the hexadecimal value is 8901. Therefore, the value that we can write it here and the question mark, it's 8901. That is how we configure the DMA channel 1 to read the ADC results. Next thing we're going to do here is to provide an interrupt source for the DMA. Since we are working for channel 1 and based on the procedure, we'll be using the ADCA interrupt 1 as a triggering source for this channel. Therefore, we can put here the value equal to 1. The value of 1 here can be located on this list of triggering source for each DMA channel. Add ka interrupt 1. After we select the DMA interrupt source, let's proceed now on the next part, which involves the DMA regs channel 1 control. This is how we configure the controls, which also the same with our mode, have 16 bits which we need to modify. And basically, on the procedure itself, it states here that DMA channel 1 control register have to clear the error and peripheral input. And the last one is to enable the channel to run, meaning will remain in its reset mode or the value equal to 0. Going back to our procedure, we have here reserve for bit number 15, meaning that's the value equal to 0. For the overflag, 0. For the run status, it's 0. Read only. No specific actions to be done as stated in the procedure. So let's put the value equal to 0 in its reset mode. The burst status, 0. The transfer status is also equal to 0. The reserve, keep it 0, 0. Next thing to do here is the peripheral interrupt flag, also equal to 0. And we have here the error clear. It states there we have to clear the error, so we have to put 1. 1 means we have to clear the error, and 0, no operation. Followed by reserve, and then peripheral interrupt clear, which has also a value of 1. And for the peripheral interrupt force, it's equal to 0. The soft reset is also equal to 0. The halt, it's not stated in the procedure, so let's keep it 0. And for the run, in order for us to enable the run, we have to put the value equal to 1. And that's the value of your DMA regs channel 1 control. The same procedure with your mode. We just have to put a double slash here, and then let's copy the value. You can copy the 0, 0 up to 7, but since it's preceded by 0, meaning it has no value, so we can start on bit number 7, which has a value of 1, and then followed by 2 zeros, and then 1, and then 3 0, and then 1. So this is now the equivalent binary components of your control registry. We just simply copy this one and convert into hexadecimal. So the value is equal to 91. Therefore, what we need to write here is 0091. Make it sure always in writing for the hexadecimal value, the minimum numbers should be equivalent to 4. That is why we have to put 0091. The 0x, that means hex. And we are now done in configuring our DMA channel. We have to Control S always after we make modification in order for us to ensure that the values we inserted on the specific program files are saved. So we have to Control S. The next thing we're going to do here is to initialize our function DMA, because in our previous examples we have to initialize specifically those prototype functions, but now we are dealing with DMA, so we have to initialize the DMA. So how to initialize the DMA? We just follow the same procedure. That's init DMA. Let's check it here. But if you want to double check that specific prototype function, you can check it here. Initialize DMA void, a replacement for your main function, because in this DMAC file, this represents the initialize DMA function loop. So let's go back to your main, and we have to check it here on the peripheral initializations. DMA initialize remains blank, so we have to put it here, init DMA, followed by 2 parentheses and then semicolon. So that's how we initialize our peripheral component, which is the DMA. And again, Control S. Our next thing to do here is to set up our PIE interrupt. At this point, we have to edit the ADC.c because previously the same file we have on our lab 6, which we use the ADC interrupt to enable our ADC. But now we are using the DMA interrupt, meaning the ADCA1 interrupt will be no longer used, so we have to comment out. When we say comment out in C files, usually that represents a comment syntax, meaning to turn part of the program into comment so that once we run the program, it will not affect. Let's double check the ADC. Just click here. So just click here the ADC and you have here. We have to locate the part wherein we enable the ADC interrupt. In disabling for an interrupt or a component or a part of your C program file, there are many ways. So we can put this one equal to 0, meaning it's already disabled. Since in the procedure we have to comment out, meaning we have to follow that procedure. But how are we going to comment out? You have just only to introduce a 2/, meaning that represents the specific line wherein the 2 slashes introduced represents a syntax node. That's why the color change. The next thing we're going to do here is to check on the DMA1 channel. After we disable the ADC interrupt, we'll find a way on how to enable our DMA interrupt. To enable our DMA interrupt, since we choose channel 1, we have to locate DMA channel 1. This value here, the DMA underscore CH1. We have to Control C and locate this value in your datasheet. As you notice, we have here the PIE channel mapping, and there the DMA underscore CH1 is highlighted, and it is located in the intersection of your interrupt x.1 and interrupt 7.y. In other words, the DMA channel 1 has an interrupt value of interrupt 7.1. But our concern here is to identify what specific group, at the same time, what specific parts of that group or within that group. So let's try to look more. And here, the DMA underscore channel 1 is located in PIE group 7 with an interrupt value of interrupt 7.1. In other words, if we have to fill in this blank here, the PIE group number is located to PIE number 7, which has an acronym code of PIE IER7. And within that group, it's interrupt 7.1. Next thing we're going to do here is to locate now or to modify the DMA.c following the data we gathered from procedure number 6. So we have to enable the DMA channel 1 interrupt using this PIE control registry. We have to copy this one and we have to write the code for DMA channel 1 interrupt. So let's go back to DMA.c. So going back here on line number 86 and 87, it's vacant, so we have to fill in this value. In writing for the code, it should start always on the device registry. For the interrupt, the device registry is always the PIE control registers. So followed by that, and then next is your group number, which is PIE IER7, and then bit, and then interrupt. So in this interrupt, just now we said that the interrupt value for DMA channel 1 belongs to interrupt 7.1. We have to locate now the PIE IER7 in our datasheet, and we have here on page 196. Specifically, the interrupt belongs for DMA channel 1 is interrupt 7.1, and we have this value here which has a field of interrupt x1. Therefore, we will put here interrupt x1 and then space equal to 1 because we are enabling the data, and then followed by semicolon. After which, we have now to enable the interrupt 7, meaning we have to provide a value of IER. The same procedure in our previous activity, you just write here IER equal the bitwise operator, or which is represented by this PIE IER7 that belongs to interrupt 7. So how we write the interrupt 7? Basically, if you have that 15 bits or 16 bits start from 0 to 15, therefore your interrupt 7 belongs to bit number 6. So writing that value, so we can therefore write this is your bit number 1. Writing in your binary to hex converter, that means we have to provide 0, 0, 0, 0, 0, 0, 0. But never mind, we just skip the 0 because it has no value. Let's start on bit number 6, which has a value of 1, and then bit number 5, 0, and then so on and so forth. So this one should have equivalent number of 7, 2, 4, 6, 7. So this is now how we enable interrupt number 7 using the binary system. And then let's just convert this one. It should be expected the value is equal to 40. So we can write it here on your CCS that the value should be 40, but it's in hexadecimal, so we have to write 0x0040 and then followed by semicolon. And we are done now on configuring our DMA channel. At the same time, the DMA interrupts and also the triggering source, and we are now ready to build to check whether there is an error in our system or in our codes. We have to Control S all files with asterisk to make it sure that all files are saved accordingly. So let's build. Just click this part. And then after we build, let's debug using this green button here. So just click debug. In debugging, you have to make it sure that you have to use the appropriate CPU. For this activity, we'll be using the CPU number 1. So uncheck CPU number 2 and click OK. After we build, then let's proceed on the debug button. Just simply click this green button here and debug. We can just wait for a few seconds. Then after we debug, make it sure that the power cycle in this activity will be using the EMU boot SRAM. So we have to double check here. So just click the script and then EMU boot SRAM. And then the next thing we're going to do here is to get a value or signal from our PWM1A, and based on our developmental kit, the PWM1 belongs to J4. And then the other one, the signal will be coming from your pin number 30, which is ADSIN AO. So we have to connect these two using a jumper wire, pin number 30 and pin number 40. After we connect the wire, we are now ready to run. In running for our system, we can use either in real-time mode or in just the typical run. Since we need to get the value in terms of real-time, we have to click this one, the script, and then real-time emulation control, and then the real-time with reset. You have the next thing we're going to do here is to locate now the memory browse, which we already have here, and then we put ADC buff. We have to include always the end, which is the ampersand ADC buff. And then we have to run this one in continuous mode since we're running in real time. So as you notice, the value is keep changing because we are running in a real time mode. And if we want to get the values in terms of analog, we can view the graph by using tools and then your graph in single time. So we have here the properties of your graph, and we can input the values accordingly based on our procedure. The acquisition buffer is equivalent to 50. So we can just put here 50. The display data type, that's equivalent to 16-bit unsigned integer. The sampling rate is 50,000. the start address still belongs to ADC buff. Make it sure to write it properly. Next thing we're going to do here is to identify the display data size, which is equivalent to 50. And the next is the time display unit, and we want it to be microseconds. So we can just click OK. You will notice that the graph appears in this one. If you want to make it sure that we really follow exactly the procedure, as accordingly it says here, that the graphical display should show the generated 2 kHz, 25% duty cycle symmetric PWM waveform. So to get that value, since we're using the time display unit, microseconds, let's check it using the marker. So just simply click this one and then put it here, and then click again and then put it here. It should be within the scale of 2000 Hz or 2 kHz. And we have here the 500. This is for one cycle, the 500 microsecond, because if you want to get the 2000 Hertz equivalent in terms of its time value, we just have to take the reciprocal of 1 over 2000, and that's equivalent to 500 microseconds. It's exactly correct. And if we want to get the continuous response of our signal here, we can easily click this one, the continuous refresh, and as you notice, the value will start to change. The same with your ADC buff. To ensure that the system is running, you can verify also using your launchpad. The LED D9 should be blinking on your launchpad. And this is how we run the DMA, on how we convert digital signals into its equivalent analog to digital or digital to analog, vice versa, without processing to the CPU. We only need here is the DMA controller to facilitate all the process. And next thing we're going to do here, we have to full halt. So if you want to terminate the program, we start first with reset full halt or simply full halt. And then after that, you have to terminate the whole system. And that's how DMA works. Thank you for listening.